Hey everyone, and welcome back to AI Paper Podcasts. Have you ever been in, say, a really noisy cafe trying to use your phone's voice assistant? Or maybe using an assistive listening device somewhere crowded?
Oh yeah, happens all the time. I just can't pick out your voice from all the background chatter.
Exactly. And that challenge, pulling just one voice out of a messy multi-speaker environment, it's super critical for so much tech today.
Right, think smart assistants, hearing aids, communication systems, and the tech designed to do just that is called target speaker extraction, or TSE.
And today, we're diving deep into a really interesting paper that proposes a new way to tackle this. It's called FlowTSE, Target Speaker Extraction with Flow Matching.
Sounds intriguing, flow matching. We'll need to unpack that.
Definitely. Our mission today is to break down this FlowTSE paper for you. We want to understand how it works, what this flow matching approach is all about, and importantly, see how it stacks up against other methods.
Okay, so before we get into the weeds, maybe a quick summary for the short form version.
Good idea. So the big picture, TSE is crucial, right? But the paper argues that a lot of the current top methods, especially the generative ones, are often really complex.
Yeah, they often kind of stitch together different pre-trained parts, which can be a bit clunky and add overhead.
And FlowTSE aims to simplify that. It introduces a cleaner, more direct generative approach using something called conditional flow matching.
It works directly with mel-spectrograms, which are common audio features. And it uses two inputs, a sample of the voice you want to extract the enrollment and the mixed audio itself.
Plus, they've got this optional add-on, a phase-conditioned vocoder, which sounds technical, but it's basically for situations where you need a super precise audio waveform output, not just something that sounds okay.
Right, and the results. Well, the paper shows FlowTSE performs as well as, or even better than, some really strong existing techniques on standard tests.
Meaning you get good quality, intelligible speech, but with a potentially simpler setup.
Exactly. High quality, good intelligibility, simpler architecture. That's the core pitch.
Okay, that's the high-level view. Now let's really roll up our sleeves and get into the details of the paper itself.
All right, so first, let's properly define the problem again. TSE isn't just noise reduction, which we often call speech enhancement, or SE.
Right, SE is about cleaning up noise from a single speaker, usually.
Correct. TSE is trickier. You've got a mix of multiple speakers plus maybe background noise, and your goal is to isolate one specific target speaker.
And the key is that you have a little snippet of their voice beforehand, that enrollment audio, to tell the system who to listen for.
Precisely. That enrollment sample is the guide. Now, the paper categorizes the ways people usually tackle this into two main families, discriminative and generative.
Okay, so discriminative methods. They're more like a direct mapping, right? They try to learn a function that takes the noisy mix and spits out the clean speech directly, or maybe it predicts a mask.
Yeah, like a filter to apply to the mixed audio to isolate the target. They basically learn output, function, input.
And they've had success, but the paper points out some downsides.
They mention that discriminative models can sometimes create weird sounds, artifacts, and they might struggle if the audio is really, really corrupted.
And maybe generalizing, like to new noises or speakers they weren't trained on.
Exactly. Generalization can be a challenge. Which leads us to the other camp, generative models.
These are different. Instead of just mapping input to output, they try to learn the underlying structure, the distribution of what clean speech actually sounds like.
Right. They build a model of clean speech. Yeah. And the advantages, according to the paper, are often better perceptual quality, it sounds more natural, and potentially better robustness in really tough, noisy conditions.
But there's always a but, isn't there? Existing generative TSE methods have their own problems.
Well, yeah. The paper highlights that many cutting-edge generative TSE systems end up being quite complex. Think multi-stage pipelines, lots of moving parts.
And a big one seems to be reliance on external pre-trained models, like massive ones.
Exactly. They often lean heavily on things like huge self-supervised learning models, SSL models trained on tons of unlabeled audio, or even full automatic speech recognition, ASR systems, just as components within the TSE pipeline.
Which must add a ton of complexity and computational cost, right?
Yeah.
Just dragging those huge models in.
Definitely. It makes them harder to train, harder to deploy, especially if you're thinking about running this on, say, a mobile device or something less powerful than a server cluster.
I was wondering about that reliance. Is it just the cost? Or do those external models cause other issues, like making it harder to train the whole thing end to end?
That's a really good point. It's certainly cost and complexity, yeah. But the paper kind of hints that just plugging these giant pre-trained black boxes into your pipeline isn't always seamless. It can create its own challenges, maybe making it harder to perfectly preserve the target speaker's specific voice characteristics, or introducing dependencies that make the whole system less flexible.
Okay, that makes sense. And they also mentioned some methods work in the complex STFT domain, short-time Fourier transform.
Right, which keeps all the phase information but is computationally pretty heavy. Training can be slower.
Whereas using mel-spectrograms, which FlowTSE does, is simpler computationally, but you lose that phase info.
Precisely. That's the classic trade-off. MELs are efficient, widely used, but they discard phase. Standard vocoders can synthesize some phase to create listenable audio, but it's not the original phase.
And losing that precise phase can make it hard to reconstruct the waveform perfectly, especially the fine timing details.
Yes, and the paper also notes that some generative models, working just from MELs, can sometimes struggle to really nail the target speaker's identity consistently, especially in very challenging mixes.
Okay, so that sets the stage perfectly. All these complexities and trade-offs in existing methods. And this is where FlowTSE comes in.
Exactly. It's proposed as a way to get the benefits of generative modeling, the quality, the robustness, but with a significantly simpler pipeline.
And the core engine is this conditional flow matching CFM. Can you give us an intuition for that? How is it different from, say, diffusion models, which have been so popular?
Sure. So diffusion models, roughly speaking, work by adding noise step by step to data and then learning to reverse that process, removing noise step by step to generate new data. It can be quite a few steps.
Okay, like iterative refinement.
Right. Flow matching takes a different philosophical approach. Instead of discrete steps, think of it as learning a continuous, smooth transformation, like a direct path or flow that morphs a simple distribution, like random noise, directly into the complex data distribution you want, like clean speech mel-spectrograms.
Huh. So less like a staircase of denoising steps and more like a smooth slide from noise to the target.
That's a pretty good analogy. And the model's job during training using the CFM objective is basically to learn the velocity at every point along that slide. It needs to predict the direction and speed required to stay on the path from the initial noise, let's call it x0, to the final target by 1.
So it learns target start, adjusted for where it is on the path.
Essentially, yeah. It learns to predict the vector by 1 by 0, given its current position x, which is a mix of x0 and y1, and the time t, how far along the path it is. It's learning the instantaneous push needed to follow that smooth trajectory.
Okay, that's conceptually quite elegant. And the architecture they use for this?
It builds on familiar components, actually. They use transformer blocks, similar to what you see in modern text-to-speech or diffusion models, with things like adaptive layer normalization.
And what are the actual inputs to this transformer?
It takes the MEL spectrogram of the target speaker's enrollment audio and the MEL spectrogram of the mixed noisy speech. These are concatenated together, usually along the time axis, and fed in.
Ah, okay. And they mentioned something specific about the attention mechanism within the transformer, something about how the different parts can interact.
Yes, that's quite clever. The tokens representing the mixed audio are allowed to attend to or look at the tokens representing the enrollment audio.
So the noisy part can get guidance from the clean speaker sample. Makes sense.
But crucially, it doesn't work the other way around. The enrollment tokens cannot attend to the mixed audio tokens.
Why restrict it that way?
Well, you want the model to use the clean enrollment sample as a fixed reference for the target speaker's voice. You don't want the representation of that clean sample to get contaminated or altered by looking at the noisy, mixed-up signal it's trying to process. Keep the reference pure.
Got it. That completely tracks. So training involves sampling time t, feeding in the MELs, and training the model to predict that velocity vector using the CFM loss.
Yep. And then for inference, when you want to actually extract the speaker.
You'd start with random noise, representing the beginning of that path at t0. Then you use a numerical solver, like an ODE solver, to integrate the learned velocity field over time, from t0 to t1.
And that integration process smoothly transforms the initial noise, guided by the enrollment audio, into the estimated clean MEL spectrogram of the target speaker at t1.
The enrollment part's job is done then. It guided the generation.
Yeah.
And finally, you pass that estimated clean MEL spectrogram to a vocoder to get the actual audio waveform.
Exactly. And a key point the paper emphasizes is that this whole FlowTSE process, the flow matching network itself, doesn't need those large external pre-trained encoders or ASR models that some other generative methods rely on.
so the main network is self-contained, just needing the enrollment and mixed melses. The vocoder is separate, of course.
Right. The vocoder is necessary to get audio, but it's typically a much smaller separate module, and it's not deeply integrated into the core extraction logic in the same way those big external models are in other systems.
That feels like a significant simplification. Less complex dependencies, potentially easier to optimize and deploy.
Absolutely. That's one of the main selling points, aiming for state-of-the-art generative quality with a less cumbersome architecture.
Okay, but let's circle back to that vocoder step and the phase issue. Mel Spectrograms ditch phase. Standard vocoders make something listenable, but the paper says sometimes you need really accurate phase.
Yeah, they argue that for certain applications, just having plausible phase isn't enough. You need phase that's much closer to the original clean speech.
What kind of applications need that level of precision?
They mention a few examples. Like, if you're feeding the output waveform into another AI system that works directly on raw audio and might be sensitive to exact timing, they mention Hubert as an example.
Okay, so for system integration.
Right. Or potentially in professional audio editing, where precise alignment is critical. And possibly even in advanced hearing aids, where preserving the exact temporal structure could be important for clarity or spatial cues.
So, for those specific cases, they proposed this enhanced vocoder, the phase conditioned vocoder. It's based on an existing vocoder model called Vocos.
Yes, they took Vocos and modified it. Two main changes. First, they added cross-attention layers into the main building blocks of the vocoder network.
Cross-attention for what?
This allows the vocoder, while it's generating the waveform based on the estimated clean mel from FlowTSE, to also look at the short-time Fourier transform STFT features of the original mixed speech input.
Wait, why look at the big speech STFT? Doesn't that have the other speakers and noise in it?
It does, but critically, the STFT contains the original phase information from the mixture. Predicting clean phase from scratch is incredibly difficult. So the idea here is clever. Use the real phase information that's already present in the mixed signal as a strong hint or guide. The model learns to leverage this existing temporally aligned phase informed by the clean magnitude information it gets from the FlowTSE output.
Ah, okay, so it's not trying to invent phase, but rather intelligently borrow and adapt the phase from the mix, guided by the clean mel estimate. That's neat. What's the second change?
The second change is in the final output layer, the part that does the inverse STFT, ISTFT, to produce the waveform. They modify it to explicitly model the phase. Instead of just using a standard phase reconstruction technique, it learns complex coefficients, learnable parameters, alpha and beta, to create a weighted combination.
A combination of what?
A combination of the phase derived from the vocoder's own internal complex representation and the phase taken directly from the mixed signal's STFT. This blend aims to get the best of both worlds.
And they train this specific vocoder using a particular metric, SISDR.
Yes, scale invariant signal to distortion ratio. And SISDR is known to be very sensitive to time domain errors, including phase alignment issues. Optimizing for SISDR directly encourages the vocoder to produce a waveform that's temporally very close to the ground truth clean signal.
And this phase conditioned vocoder is trained separately, right? Not end-to-end with the FlowTSE part.
Correct. It's trained independently using pairs of clean mel spectrograms and the corresponding mixed STFT features from the training data. It's a specialized tool just for that high-fidelity waveform reconstruction task.
Okay, method clear. Core FlowTSE doing the heavy lifting on MELs via CFM, and then this optional specialized vocoder for cases needing precise phase. How did it all perform in their experiments?
They tested it pretty thoroughly. They used standard data sets, Libre speech for clean speech, WAM for noise, and evaluated primarily on Libre 2 mix, which has controlled two speaker mixtures, both clean and with added noise.
They varied things like the signal-to-noise ratio, the speaker overlap, how long the enrollment clip was.
Yep, covered different scenarios.
Yeah.
And they evaluated using a whole battery of metrics.
Let's see, PESCAS and ESTOI. Those measure perceived quality and intelligibility, but need the original clean speech for comparison, right?
Exactly. Those are intrusive. Then OVRL and DNSMS are non-intrusive, meaning they estimate overall quality and noise level just from the output audio.
They also used word error rate, R, from feeding the output into a Whisper ASR system that's a proxy for intelligibility. And speaker similarity, SIM, to check if it sounds like the right person.
And SISDR specifically for the phase-aware vocoder evaluation.
So looking at the main results for multi-speaker TSE, like in their Table 1 and Figure 2, how did FlowTSE do?
It performed really well. Across both the clean mixes and the noisy ones, FlowTSE consistently matched or even beat several strong baseline methods, including other generative models and discriminative ones.
Any specific metrics that stood out?
Well, it achieved the highest PESQ score in their main comparison table, which suggests good overall perceptual quality. The speaker similarity, SIM scores, were also very high, indicating it preserves the target speaker's voice identity effectively.
And the WER results. I remember this was particularly interesting in the figure comparing it against WhisperT.
Oh yeah, the WER results are quite striking. FlowTSE significantly outperformed WhisperTS, a model with a similar parameter count, but maybe more impressively, its WER was very close to WhisperTL, which is a much larger model.
And WhisperT was specifically trained using an ASR loss, right, to optimize for intelligibility.
Exactly. WhisperTSE was basically spoon-fed the answers by being optimized directly for ASR transcription accuracy. FlowTSE, without that direct ASR supervision, achieved comparable intelligibility just by generating a high-quality mel spectrogram through flow matching.
That's a really powerful result. It suggests you might not need that explicit complex ASR integration if the core generative process is strong enough.
It really does. It speaks volumes about the effectiveness of the flow matching approach for producing intelligible speech.
They also did a cool experiment applying the same FlowTSE model, the one trained for multi-speaker TSE, directly to a single-speaker speech enhancement task. No retraining.
And even though it wasn't trained specifically for SE, it performed exceptionally well there too. It got the best PASQ, OVRL, and DNS-MOS scores in that SE comparison, Table 2.
Shows robustness then. The model learned general principles of clean speech extraction.
Seems like it. Good generalization beyond its specific training task.
Okay, and lastly, the phase-aware vocoder results in Table 3. Did it deliver on the promise of better phase reconstruction?
Yes, the results there are clear-cut. Using the phase-conditioned vocoder led to a really significant improvement in SISDR compared to using a standard mel-based vocoder with the same FlowTSE output.
So it definitely achieves better temporal and phase alignment, as measured by SISDR.
Absolutely confirms its effectiveness for that specific goal.
Although the paper does mention a slight trade-off, right? The phase-conditioned one might slightly lower scores on metrics like PASQ or OVRL compared to a top-tier standard vocoder.
That's right, there can be a small trade-off. So the paper concludes that the choice really hinges on your downstream needs. If you absolutely need that precise waveform fidelity, maybe for integration with other systems or specific audio processing, the phase-conditioned vocoder's SISDR benefit is key.
But if general perceptual quality is the only goal, a standard high-quality vocoder might still be the way to go.
Exactly. It gives you options depending on the application.
All right, so let's pull it all together. Based on the methods in these results, what's the main contribution or takeaway from the FlowTSE paper?
I think the core message is that they've introduced a novel and, importantly, effective generative approach for TSE using flow matching.
And a huge part of that novelty is its relative simplicity, especially compared to prior state-of-the-art generative methods.
Definitely. Reducing that complexity, avoiding the need for those massive external pre-trained models, that's a major theme and a practical advantage they highlight repeatedly.
And yet, despite being simpler architecturally, it delivers high audio quality, strong intelligibility, good speaker preservation, performing right up there with, or better than, the complex baselines.
Yep. So the paper really positions FlowTSE as demonstrating a promising path forward, showing that you can achieve top-tier generative TSE results with more streamlined and elegant approaches.
So wrapping up our deep dive into FlowTSE, it seems like leveraging flow matching directly on mel-spectrograms is a really powerful technique. It offers this surprisingly straightforward yet highly effective route to high-quality target speaker extraction. It's a fantastic illustration of how simplifying the generative pipeline can yield excellent results.
It really is. And that leaves us, and you, with a final thought to chew on. We saw FlowTSE simplify TSE and even perform well unexpectedly on SE using flow matching. Where else could this kind of approach, simplifying complex generative tasks using flow-based methods, make a difference? Could it streamline other challenging audio processing problems, or maybe even tasks in other domains like images or video that currently rely on very complex cascaded models?
And perhaps more critically, what could that simplification mean for actually deploying these kinds of powerful AI models? Could it make high-performance generation more feasible on everyday devices, bringing these capabilities out of the lab and into more people's hands? Something to think about.